students, welcome to Sunil's tutorial. I'm Sunil Nirwani and today we'll be doing this chapter called as wave theory. Now, last lecture we had seen what is polarization of light. Now let us see how do I polarize light. Now when a natural unpolarized light is incident on a material called as calcium or calcite quartz crystal, the ray splits into two refracted rays, and this phenomena is called as double refraction, or it is called as birefringence. When a ray of light is incident on a calcite crystal, suppose if I have this, this is your ray of light. Let us assume that this is your ordinary ray of light, which has vibrations in all the directions. Right? This is your calcite crystal. So this is how ray of light is moving. It's in all the directions. Right? Now when it passes through calcite crystal, it splits into two. Right? You have double refraction taking place. One, you would have refraction and it will come out, and you will have another refraction and it will come out. One of the ray is going to be like this and the other ray is going to be this way. Right? Out of the two rays, one is called as the E ray and the other is called as the O ray, and this is called as the calcite crystal. Right? Now let us try to see the front view of the rays. This was a cross section I'm showing you. This is how I'm sending light and this is how they are splitting. Now let's see the front view. If I see from that side, how will it appear? This is going to be my calcite crystal, and I would have a ray in the center. That's your O ray would be in the center, and I would have E ray rotating in a circle around the center as your angle of incidence changes. This is my E ray. Right? That's your top view. This is your crystal. So that means there are certain substances, when ray of light passes through them, instead of refraction, you have double refraction taking place. Right? Do we get this thing clear? Now, in that case, you get two types of images. One is called as O ray, which is called as an ordinary image. The refracted ray that produces this image is called as the O ray. The other image, which rotates around the first image, this image is called as the extraordinary image. Right? And it rotates around the ordinary image. Now, the ordinary ray, the ordinary ray is found to obey all the laws of refraction and travels with the same speed in all directions. So this is like your normal ray of light. And let us assume that its refractive index is mu0, and it is going to be constant for the crystal. The other ray that you get, E ray, that's the extraordinary ray, it does not follow the laws of refraction and it does not lie in the plane of incidence. Right? Its value, for a given value of angle of incidence, you have a value of angle of refraction for extraordinary ray, which depends upon the direction and the ray from which the incident ray is coming. Right? So these are the two types of rays that you can get when a ray of light, ordinary ray of light, passes through a calcite crystal. Right? Let's see this. When an unpolarized light is incident on a calcite or quartz crystal, the ray splits to two refracted rays, right? And this phenomena is called as double refraction. Is called as double refraction. Fine. Now, if the crystal is rotated about the incident ray, if the crystal is rotated about the incident ray axis, if the crystal is rotated about the incident ray axis, then one of the two images remains stationary. Then one of the two images remains stationary, right? And this is called as ordinary image. Called as ordinary image, right? So as I rotate the crystal, one of the image will remain stationary, and that is called as ordinary image, or which is called as which is produced by the O ray, right? The other image rotates around the first. The other image rotates around the first and is called as the extraordinary image. Extraordinary image, which is called as the E, which is produced by the E ray. Fine, do we get this thing there? So you have two types of images produced: ordinary image and extraordinary image, right? The ordinary ray, the O ray, obeys the laws of refraction. Laws of refraction, and travels with the same speed in all directions. And travels with the same speed in all directions, right? Now, therefore its refractive index, therefore the refractive index of the crystal is constant for the ordinary ray. Therefore the refractive index of crystal is constant for the ordinary ray, O ray. Right, that's your ordinary ray, the simple normal refraction. The extraordinary ray, the E ray, does not obey laws of refraction. It does not lie in the plane of incidence, and does not lie in the plane of incidence. Right? For a given value of angle of incidence, or a given value of angle of incidence, the value of angle of refraction depends on value of angle of refraction depends upon the direction in which the ray is incident. Or the direction in which the ray is incident. Fine, do we get this in here? Now, therefore the refractive index of the crystal for extraordinary ray is not constant, I can say, since it's going to depend upon the direction in which the ray is incident. Therefore I can say that the refractive index of the crystal is not for E ray is not constant. Another important feature here is that both the ordinary ray and the extraordinary ray are polarized in planes which are mutually perpendicular to each other. Right? So the two rays are going to be in two separate planes, and such that the two planes are going to be perpendicular to each other. The ordinary ray and the extraordinary ray are polarized in two planes which are perpendicular to each other. So this is an inherent property of crystal, that it gives you double refraction, right? Now let us try to understand more about this crystal. So in the case of crystal, you are going to get two rays, two refracted rays, and the two rays are going to be in two planes which are going to be mutually perpendicular to each other, right? Now let us try to understand the structure of this crystal. The crystal structure is rhombohedral, right? It has 6 faces of a parallelogram, having each face having an angle of 102 degree, right, and 78 degree. The two opposite corners at which the 3 angles are obtuse is called as the blunt corner of the crystal. So you will have, see, if you have this way, this is going to be 102 degrees here, this is going to be 78 degrees. This corner is called as the blunt corner. Fine. Now, the line which passes through the blunt corner and is equally inclined to the 3 edges of the corner represents the optic axis. So if I have a line passing through there, right, and if it is equally inclined to the 3 axes, then this line is called as the optic axis. So what is optic axis? Optic axis of a doubly refracting crystal is that particular direction along which the ordinary and the extraordinary ray travel with the same speed. So this is that direction in which both the ordinary and the extraordinary ray would travel in the same speed. Fine, do we get this in clear? Now, a crystal which has only one optic axis is called as uniaxial crystal. There are crystals that have 2 optic axes and they are called as biaxial crystals. Fine, do we get this in clear? Now, the plane containing the optic axis and perpendicular to the opposite faces. So there will be a plane that will contain the optic axis and it will be perpendicular to 2 opposite faces. That plane is called as the principal plane. Fine. So do you understand the structure of a crystal? Let's just write this down. That's how your crystal would be. Now this, let's name this as M. Let's call this point as N. So this particular axis that is going to pass through point M and N, this is called as your optic axis. Fine. This angle here is going to be 78 degrees. Right. This angle here is going to be 102 degrees. Fine. So, that's how your crystal structure is. So let's write the crystal structure down. I can say that the crystal structure is rhombohedral. Right? Having 6 faces, each face being a parallelogram. Having 6 faces, each face being a parallelogram. Right? Having an angle of 102 degrees and 78 degrees. Having an angle of 102 degrees and 78 degrees. Right? The two opposite corners at which the 3 angles are obtuse, those corners are called as blunt corners. The 2 opposite corners at which the 3 angles are obtuse are called the blunt corners. So here this is one blunt corner, and I need another blunt corner where you have obtuse angle. So this is going to be the other blunt corner where you have obtuse angle. Fine, do we get this in here? Now, once you have this, the line that passes through one of the blunt corner and is equally inclined to the 3 edges, the line passing through one blunt corner and equally inclined to the 3 edges meeting at that corner, is called optic axis. And in this case, this is the optic axis. Right? So that is going to be your optic axis. Right? Now, optic axis is that particular direction along which the ordinary ray and the extraordinary ray travel in the same speed. Optic axis is that particular direction along which the ordinary ray and extraordinary ray travel with same speed. Right, that's the only direction. Now, you can have crystals with one optic axis, or you can have crystals with 2 optic axes. Now, the plane containing the optic axis, the plane containing optic axis and perpendicular to the opposite faces of the crystal, opposite faces of the crystal is called the principal plane or the principal section. Fine. So do you understand the structure of the crystal? Now we are going to see a very specific crystal which is called as a Nicol crystal, or which is also called as a Nicol prism. Now, a Nicol prism is a device which is used to produce and analyze a plane polarized light. This particular device was designed by William Nicol in 1928. Now, how did he make this, and why do we have, or what is so specific about it, that it is used for producing and analyzing a plane polarized light? The underlying principle of Nicol prism is that the two refracted beams in a doubly refracted calcite crystal can be produced by total internal refraction. The reason why I did this double refraction is because I need this in Nicol prism. In Nicol prism, what did he do? He said that I can remove one of the two refracted beam by total internal refraction, and both being polarized. After elimination, you will have only one beam left. So his principle was that you have two rays, the ordinary ray and the extraordinary ray. He would remove the extraordinary ray using total internal reflection, and you would have a plane polarized light which would be an ordinary ray which would follow all the laws of refraction. That's the whole principle of a calcite crystal or a Nicol prism that he would be using, right? Now, so construction, let's see a construction of Nicol prism. Now let's see the front view of this. Same calcite crystal only is taken. This angle is 71 degrees. This angle is 68 degrees. This angle is 71 degrees. And this is 90 degrees. Right? Let's consider that you have A, B, C, D. How do I make a Nicol prism? Right? To make a Nicol prism, first I need to take a calcite crystal whose length is 3 times its width. Right? A calcite crystal with length equal to 3 times the width. So that specific calcite crystal has to be taken. Now, the smaller faces A, B and C, D of the principal section are ground at angle B. The smaller faces A, B and C, D are ground until the angle at B and D, until the angle GROUND are ground until the angle at B and D is reduced from 71 degrees to 68 degrees. Right? So I'm going to do filing of this. I'll file this off. I'll file off the crystal till the time I get an angle which is equal to 68 degrees. Right? So now the crystal is cut into two halves by a plane passing through the two blunt corners. After you've done this, the crystal is cut into two halves by a plane passing through its two blunt corners. Right, blunt corner means where you have obtuse angle. Right? Now once you have cut this, that means I'm going to cut it along AC. Now once I cut it along AC, then the cut surfaces of the two halves are polished to make them equally flat. The cut surfaces of the two halves are polished to make them equally flat, right? So I've cut this along, then I've polished the two surfaces, right? Then they are again, after I cut them, I polish them, then I'm going to stick them back with a glue, right? But there's a very specific glue that has to be used to stick them back. Why, we'll see that later, but first let's just see the construction. So they are then cemented together into original. They means the two halves are then cemented together by a thin layer of transparent adhesive called, there's this specific adhesive that has to be used, and the name of this particular adhesive is Canada Balsam, right? So they are going to be stuck together with this layer. Then the sides of the crystal are blackened with lamp black layer to absorb ordinary light. The sides of the crystal are blackened with lamp black to absorb ordinary ray. Right? That's how you make a Nicol prism. Right? So you take a calcite crystal whose length is 3 times its width. You file the two short faces till the time the angle reduces from 71 degrees to 68 degrees. Cut the crystal along principal axis, polish the two surfaces, put a thin layer of glue, which is your Canada Balsam, and stick it together. And the sides, the two long sides, you're going to blacken it with lamp black. That's it. Fine, do we get this thing clear? Why do I do all this? How does the Nicol prism work? Working of the Nicol prism. Let's see how does it work as a polarizer. Right? Now, let's draw the Nicol prism. Right? That's your Nicol prism. You would have a ray of light that would pass through. Due to bifringence, the ray of light would split into two. There would be double refraction taking place. Guys, I just explained to you, that's the inherent property of the crystal. The inherent property of crystal is that it will give rise to bifringence. Right? Now, I'm going to design it in such a way, this whole angle and the Canada Balsam is designed in such a way that one of the ray, as the ray moves, it moves from a denser medium to a rarer medium, and it moves at an angle greater than the critical angle. Since it moves from denser medium to rarer medium at an angle greater than critical angle, one of the ray is going to get totally internally reflected. There is going to be total internal reflection of one of the ray. So as a result of which, it is going to get reflected. The bottom face is coated with lamp black. Lamp black will absorb the entire ray and the other ray will pass through. Right? So here you have ordinary light. Here you have ordinary light. Now this is going to split into O ray and E ray. One of the rays is this, the other is this. Right? One of the ray gets totally internally reflected and the other polarized ray passes through. That's the basic working of a Nicol prism. Now why does this happen? Let's try to understand this. I can say that why is it going to work and how is it going to work. Here it is working as a polarizer. Right? Now I can say that the refractive index of the calcite crystal, the refractive index of calcite crystal for extraordinary ray in the direction perpendicular to the optic axis is 1.486, right? And along optic axis is 1.658, right? That means if the extraordinary ray is perpendicular to the optic axis, its refractive index is going to be 1.4 something, and if it is parallel to optic axis, its refractive index is going to be 1.6 something, right? That means I can say that the refractive index of the extraordinary ray varies between 1.486 to 1.658 depending upon the direction of the extraordinary ray. So that's the minimum and maximum refractive index that the extraordinary ray is going to have. Fine. Next, the refractive index of the calcite crystal for ordinary ray. The refractive index of the calcite crystal for ordinary ray is 1.658. Fine. That means the refractive index of the ordinary ray is 1.658. Right. Now, why did we choose Canada balsam? The refractive index of Canada balsam is 1.55. These are your three refractive indexes, and all these refractive indexes are calculated for sodium light having a wavelength of 5893 Armstrong units. All the above refractive indices are calculated for sodium light of wavelength 5893 Armstrong unit. Right? So now that I know refractive indices, let's see how refraction and internal reflection takes place. Right? Now let's consider that I have an unpolarized light incident on one end of the face AB. This is my face AB on which you have unpolarized light incident, right? Consider an unpolarized light light incident on one end face. Right? Now, one end face of the Nicol prism, right? It will undergo double refraction and will split into ordinary ray and extraordinary ray. It will undergo double refraction and will split into ordinary ray and extraordinary ray. Double refraction will take place. That's the first thing that I've shown you. In the diagram, that's the ordinary ray coming in. As soon as it enters the calcite crystal, you have double refraction taking place, right? Now for this beam, the refractive index of for this beam of light that is entering, the refractive index of Canada balsam, the refractive index of Canada balsam, we know is 1.55, and for ordinary ray it is 1.658, right? That means the ray of light is passing from, the ordinary ray is going to pass from refractive index 1.658 to 1.55. The ordinary ray is going to pass from refractive index 1.658 to 1.55. That means it is going to pass from a denser medium to a rarer medium. The ordinary ray is going to pass from a denser medium to a rarer medium, right? So I can say that thus the ordinary ray passes from denser medium to rarer medium, right? It passes from denser medium to rarer medium. Now, the ordinary ray falls on the Canada balsam at an angle greater than the critical angle. The ordinary ray falls on the Canada balsam at an angle of incidence greater than the critical angle, right? How do I find this out? What will be the critical angle for the ordinary ray? Critical angle is going to be nothing but sine inverse of 1.55 upon 1.658. That means it has to be 69 degrees. So I have to make sure that we know that the critical angle for Canada balsam is 69 degrees. So I'm going to make sure that my angle of incidence is greater than 69 degree, right? And greater than critical angle, which is 69 degree, and hence suffers total internal reflection. Right? The ray of light suffers total internal reflection. It is absorbed by the blackened face. It is absorbed by the blackened faces of the crystal and illuminated. right? So the ordinary ray is out. Now let's see the extraordinary ray. Now for extraordinary ray, the refractive index of the crystal is 1.4 something, 1.486, and the refractive index of Canada balsam is 1.55, right? That means it is going to pass from a rarer medium to a denser medium. Hence, the E ray passes from rarer medium to denser medium. Right? If it is going to pass from rarer medium to denser medium, it gets refracted and transmitted through the Canada balsam. Hence, it gets refracted and transmitted through Canada balsam. Right? Now once it is through the Canada balsam, there is a single beam of polarized light that will come out through the section. Hence, a single beam of light polarized in the plane perpendicular to principal section of the crystal emerges. Right? That's how you get a plane polarized light. Right? So that's how a Nicol prism acts as a polarizer. It gives you a plane polarized light. Light enters the Nicol prism, it gets split into two, ordinary and extraordinary light. The ordinary light suffers total internal reflection. The extraordinary light passes through and you will get your single beam of light. As soon as it enters Nicol prism, it gets polarized. Right? One of the polarized light emerges, that's your extraordinary light emerges, and the ordinary light gets total internal reflected, right? And hence it is eliminated, right? Do we get this thing here, how Nicol prism works as a polarizer? Right, we will stop this here for the day. Thank you very much.